Ma'am, is it visible?
Yes, yes, sir, it is visible. Hello?
Maybe some. Ma'am, can you hear me?
Yes, sir, it is visible, sir.
Okay.
Sir, are you sharing the slides now?
Yeah, I'm sharing the slides, but I think some technical issue. Let me stop the sharing and share again.
Okay, sir. Okay, sir.
Now, is it visible, ma'am? Okay. Before starting the lecture, first of all, I want to greet all the organizers and the participants from different parts of the world, different colleges and the universities. Assalamu alaikum wa rahmatullahi wa barakatuh. Good evening to one and all. Already my profile has been explained by Dr. Sayyid Hosna. Um, so this is my topic: quantum gates, circuits, and algorithms. I will be giving only the some brief idea on this. What is the quantum gates, the circuits, and the algorithms used in the quantum computing. Before going to the quantum gates, actually, can we discuss about the quantum computing? In the previous session, already you have discussed about the quantum computing and the eminent speakers that are Jai Prakash and another speaker has been explained the different concepts. Okay, one is the quantum computing and the quantum mechanics. So the quantum computing is very popular in the world nowadays in the IT sector. This computer is a machine which will perform the calculations based on the law of the quantum mechanics. So here we are concentrating on the particles which are in the atomic level. So this is very fast compared to the other computers, and here we are implementing the concept on the qubits instead of the bits. It is qubits. Qubits is the quantum bits. So we are concentrating on the bit as denoted by two options, 0 and the 1. The instead of working only on the bits, the quantum computing will concentrate on a large number of quantum bits, which we call as the qubits. The advantage is we are having so many advantages for the quantum computing as we discussed in the previous sessions. Okay, like we are having the large scale computers, we are having the quantum physics, the quantum mechanics. Okay, and the algorithms are very fast for searching. So these are some of the advantages. I don't want to go depth in the previous one. Now we concentrate on the quantum logic gates. So here, the before going to the quantum logic gates, it is almost similar to the classical logical gates. In the classical logical gates, we have the gates like the OR gate, AND gate, OR gate, and the NAND gate, XOR gate. These are the some of the gates. So similarly, the quantum computers. So in the quantum computing, we are using the new technology called the quantum logical gates. These quantum logical gates will perform their operations on the small number of quantum bits. Instead of small bits, we are using the large number of bits, and these operations will be performed on the large number of bits called the qubits. So these logical gates are forms like the building blocks for the quantum circuits, and here it is possible that all the quantum logic gates are the reversible gates. Okay, so these will be generated from the input of the derived output state. For example, if I pass one input, whatever the output state we are getting from that, we are generating the another output. Okay, so this might be reversible also, vice versa. So in the traditional logical gates circuits, we use the transistors to build the digital logical gates, which will be based on the electronical signals. But in the quantum logic gates, it is working on the qubits, which are more than the ions. So instead of the signals, we make the ion. So as per our chemical terminology, we are having the anion and the cation, like the positive ions and the negative ions, which we call the charged atoms. So these quantum logic gates will concentrate on the uh, tapped ions, which are known as the charged atoms. Each ion which has the two atomic states. Okay, one is the subatomic components. Here, the properties which are unique to the quantum are known as the spin, and these are very different. And we are having the interference. Interference will be one property which will cause the disturbance or the noise which will affect the state of the qubit. Okay, in order to avoid this one, we are using the one property called the protection from the interference. This is the representation of the qubits. The two states is denoted by the 0 and the 1 in the quantum. Instead of normal 0 and normal 1, we are concentrating on the vector. So this 0 vector and the 1 vector, the 0 vector indicates the ground state and the 1 vector indicates the excited state. So the qubit is represented or implemented in the two types of the energy levels of the atom. One is the ground state, which is represented as the 0 vector, and the another state is the excited state, which is represented with the 1 vector. There is one small picture available here. This is the nucleus, and in the nucleus you can see this is particle is known as the one atom here, and here there are two states represented with the ellipse. One is the ground state, which is the initial near to the nucleus, and then we are having the excited state. After some pulse of the frequency lambda is implemented for some time interval, this ground state will be converted into the excited state. So the first circle, the first ellipse near the nucleus is known as the ground state. The atom will be moved from ground state to the excited state after some time interval by implementing some pulse, some force. So this one is the state 0 vector and state 1 vector. State 0 vector is treated as the ground state, and state 1 vector is treated as the excited state. Next, representation of data superposition. So here we have the superposition, the same format. Okay, this is the 0, and here we are concentrating on the 0 plus 1. So this is already explained by the last session. Okay, so I will not concentrate on this one. So this is the one qubit. In the one qubit, we are presenting in the mathematical abstraction, and this is the vector in the two-dimensional vector space, which is known as the Hilbert space. The notation are the three options we are having here. One is the Kate notation, which is known as the column vector, and another one is the Braun notation, which is known as the row vector. So the qubit can be represented either in the column wise or in the row wise, and the column vector is represented as the Kate notation, and the row vector is known as the Braun notation. In the Braun, we are having the dual vector, which is known as the transpose on the complex. So here in the picture, we are having the spin here. You can see the phase where we have the two ions, which is known as the positive and the negative. So these two ions will be interchanged. So whenever you are applying some polarization like the left rotation or the right rotation, the left polarization. So depending on that, the spin, the uh, charge will be changed. Next, this is one notation. The qubit will be represented in the superposition state, which is represented in the vector. This is the block sphere with pointing with the Euler angles. So the two probabilities we are representing with the angles here. This is known as the Euler angles. So this is the one vector and this is the zero vector. Next, unitary matrix. The logic gates, whenever implementing on the qubits, these qubits operations will be implemented in the unitary matrix. A unitary matrix is a square matrix which represents the complex numbers, which is used to represent the quantum gate. If you are considering 2 power n into 2 power n unitary matrix represents, then it represents the number of operations on the qubits, the n number of qubits. Example, for example, if I implement on the one qubit, okay, if I consider n is equal to 1 as a qubit, then I will be using the 2 by 2 matrix. This is a 2 by 2 matrix as in the example. If I use 2 qubits, then I have to use the 4 by 4 matrix. If I use 3 qubits, then I have to use the 2 power cube. So 2 power 3, it is known as the 8 by 8 matrix. So as the number of qubits are increasing, the matrix will also change. Okay, the size of the matrix will also be changing. So this is known as the representation of the unitary matrix, what the operations we are performing on the qubits. So if any operation is performed on how many number of qubits, that operation can be stored in the unitary matrix. This is the entanglement, which is the very elegant, and this is first given by the German term Vers Skrangut by the Schrödinger, who was the first person to recognize the quantum effect. So in this one, the it contains no information about the individual particles, but it contains the opposite states, which is the superposition of the equally possible states. The entanglement, the main concentration of the property of is it is the measurement of one particle that influences the state of the other particle. So if any particle is influencing the another particle, that measurement is considered as the main property for the entanglement. And the Einstein called this property as the spooky action at a distance. Like we have so many factors associated in the universe. If we take Newton's third law, okay, depends on the action. Okay, if you move for the motion, okay, so if any disturbance is coming, it will be affected. So like this, if one particle is influencing the other particle, that measurement is the main property for the entanglement. The main advantages of this entanglement is it increases the computing power and it enables the quantum communication protocols. So this is the what we can say. This is the normal conventional classical gates where we are having the ion gates. So in the quantum physics, whenever we are using the ion gates, okay. So depends on the output here. The information which we are getting, it can be destroyed. So to avoid these type of problems, then the quantum gates are designed such that the problems which are available through the classical gates, those can be overcome. Okay, the main problem is the destroyable of the superposition of the qubits. Working of the quantum logic gates, how the quantum logic gates will work. These quantum gates will manipulate one or two bits to change the qubit's quantum state such that which will employ the superposition and entanglement to tackle the multiple operations simultaneously. These quantum logic gates are used to process the complex quantum algorithms. Unlike the classical logical gates, these are designed in such a way that most of the common complex situations are to be handled and to be overcome by using these gates. As I discussed, this is the different types of logical gates. So when we are using the classical gates, then we have the OR gate, NOR gate, NOT gate, AND gate, and the NAND gate. So these are the some of the logical gates which we are using when we design the circuits for the convention or the classical digital circuits. So as we in the previous slides we have seen some of the problems associated with these classical gates. So to overcome that one, we have to use some new technology which is known as the quantum gate designs, which is varied from time to time. Okay, so here in this design, we are going to handle one or two qubits where we apply the different effects to the qubits to produce the distinct processing outcomes. So you can consider any number of qubits. It depends on your system configuration. Okay, as we discussed in the previous sessions. So depending on the designment of the hardware, and you can take any number of qubits, and you can implement the designing of these gates. The multiple quantum logic gates will combine the logic circuit, which will be the part of the quantum computer, which is capable of managing incredible sophisticated quantum algorithms. So here we have so many quantum algorithms through which the quantum computing, the quantum gates will be used. We discussed in the coming slides. Okay, so these are the different types of logic quantum logical gates which will be implemented in the quantum computing. A few of them are poly X gate. This is the gate which will be concentrating on only one qubit. So instead of multiple qubits like 2 qubit or 3 qubit, when we are working on only a single qubit, 1 qubit, then some of the gates are these are the one of the gate poly X gate, which is denoted by the symbol called X symbol, and this will perform the reversible operation on the qubit. It is like the NOT gate. Okay, if you have 0, it will be converted into the 1. If you have 1, it will be converted into the 0. So this is like the symbol of this one. Okay, so here the X gate, it will concentrate only on one qubit, and it will perform the reverse operation. If you are performing the operation on the 0, the result will be the 1 vector. If you are concentrating on the 1, it will result into the 0. Similarly, we are having the poly Y gate. Instead of the reverse operations, this is denoted with the letter called Y. This will perform on the reversal operation plus the phase reversal. Means from positive ion, it will be changes to the negative ion, and negative ion to the positive ion. So on single qubit, on one qubit, whatever the phases are there, okay, that phase will be changed, that phase can be changed by using the polygate. So this is the poly Y gate, which is concentrating on the reverse of the phase. Next one is poly Z gate. This poly Z gate is denoted by the letter called the Z. A poly Z gate performs a phase reversal operation on a qubit, and it will add around 180-degree phase shift. Okay, so this is the another type of the gate which will be concentrating on only a single qubit. So these are the three different types of gates: poly X, poly Y, and poly Z. Next one is we are having the another gate called the Hadamard gate. This Hadamard gate is represented by using the letter H, and this gate will represent transforms the qubit from its current state to the superposition of the possible states. Okay, so it reverses the state. Next one is the phase gate, denoted by the P or the S, which will be depending on the pi by 2, that is the phase shift to apply in the qubit state. Next one is we have T gate or the pi by 8 gate. So this will be concentrating on the same phase shift which will be applied for the pi by 4 or the pi by 8 to the qubit state. and these are denoted by the letter T. So these are the some of the quantum logical gates which will be operated on only one qubit. For the reversal of the bits, the 0 to 1 and 1 to 0, the phase can be changed, and then the pi by 2 states can be applied. So these are the some of the logical gates. Next, we are concentrating on the qubit, which is the 2 bits. So instead of one qubit, if you are performing on the 2 qubits, the operation, then we have some other different types of logical gates. So the first one is controlled NOT gate, which is represented with the C naught. Okay, this will perform the operations on the 2 qubits. One is the data qubit and the control qubit. These are used to provide a conditional NOT gate. Before going to this one, I want to add one more point in the Hadamard gate. If you use two Hadamard gate combination, means simultaneously, for example, I am generating the 0 input and I am using the Hadamard gate which generates 1. Okay, again, if it generates another Hadamard gate, it becomes the 0. So the state will not be changed. It becomes, if you use simultaneously two Hadamard gates, the position will be remain same and it will work like a NOT gate. Now, this is the controlled NOT gate, which is concentrating on the operations on the 2 qubits. Here, one qubit is for the data qubit, and second one is for the control qubit. So this is providing the conditional NOT gate. The state of data qubit depends on the state of the control qubit. So if the control qubit is want to perform anything, it will be in the um, value depending on the control qubit. If the NOT gate, C NOT gate will not do any changes if it is remains the same. Okay, in the control bit. Another logic gate is control Z gate, which is known as the CZ gate. This is also used to perform on the operations on 2 qubits by using the same data and the control. Instead of the bits, we are concentrating on the phase. This will shift the phases. Okay, so depending on the value of the control qubit, if the qubit value is in one state, then this CZ gate will not change anything and it will pass the data qubit to another without any changes. If the value is in another state, okay, then it will apply the operation and the phase shifting and the interference will be applied. So this is one small table which will demonstrate the different types of gates, the symbols used, and a few of the description. First one is the identity gate. This gate usually most of the designers will not use, but it's recommended that the identity gate has to be used in designing any gate whenever required. It is represented with the symbol I. Does not do anything, but it's only like a placeholder. Like it is stored as the identity matrix called 0, 1 and 1, 0 like this. So this is the identity matrix. So most of the designers will ignore or will not use this gate when designing any circuit diagram. So the recommendation is better to use this identity matrix because it will not change anything. Okay, it's a neutral. So wherever required, it can be used. Poly X, this is the another gate and represented with the X, which is the summary we discuss here. This is used for the bit flipping, which is like the same works like a NOT gate in the classical or the convention digital logical gates. Next one is we have the poly Y. Poly Y is another form of the gate which is concentrating on only one qubit. It is represented with the letter Y, and here it is performing on two things. One is the bit as well as the phase. The two things will be flipped. Next one is the poly Z. This is the notation. Z is the notation for the poly Z, which will flip only the phase. Next one is the Hadamard. Okay, so which is the H symbol, which puts the qubit into the superposition. Phase gate denoted with the S symbol, which will add the pi by 2 as the phase. The phase will be converted into the pi by 2 of the multiplied with that one, and it will be added. Next one is T gate, which is represented with the T symbol, which is used to add the pi by 4 phase. The last one is the rotation gate. So in the slide I missed it. So this rotation gate we will rotate by using the some axis. Okay, so here we have three rotation by using three axes, x, y, and the z. By using one angle, that is the theta angular. Okay, so the qubit will be rotated in the block sphere around the x, y, or z axis. Next, this is the another one. So here we use the swap gate or the Foley gate. So these will can work on the two or the more. So the swap gate will work on the two data qubits to exchange the states, such that the uh, states will be interchanged. Swapping is a fundamental element for the quantum algorithms and the information processing for the quantum. So this gate works on the data two data qubits to exchange their states. Next one is we have the CC naught or top gate, which is known as the Toffoli gate. This Toffoli gate will operate the operations on the three qubits. So here we use the 8 by 8 unitary matrix. So here we'll be having one data qubit and two control qubits to perform the NOT operation and the data qubit depending on the two control qubits. The Toffoli gate will not change the data qubit if both qubits are in the one state. If they are in the different states, it will not perform the NOT operation. So this Toffoli gate will concentrate on the three qubits. This is some of the description of the previous explanation, the tabular format. Okay, so here we have the C naught, swap, control Z and control U, the CZ and the CU applications. Okay, this is for the Foley operation. This is the another table where the symbols are available and the gates are available with the matrix format. So for poly X, we are denoting with the X symbol followed by the gate, that is single one we are using on single qubit. Then we have the poly Y, poly Z, the Amar, the same notation, the symbols X, Y, Z, and the H. And here you can see the matrix represented. Okay, so the 0 1 1 0 means that is the matrix where we can flip the bits. Coming to the poly Y, it is denoted with the minus I, where we are having the phases as well as the bits will be swapped. In the Z, only the phase will be swapped, the flip, and the is represented with the matrix. One phase will be represented with the minus symbol. Okay, so it is the minus one. In the Hadamard, the notation will be represented by using the square root, that is the 1 by root 2, okay, followed by the 1, 1, and 1 minus 1. This is the matrix for the Hadamard notation. For phase S and P, okay, we are having the S gate, we use 1, 0, 0, I. Similarly, we are using the T gate where the pi by 8 will be implemented. Okay, so this is exponential power of E into I pi by 4. So next one is we are using the NOT gate. So in the NOT gate, the two gates will be combined. So one will be available like this. Here we use the number of matrix since it is used in the matrix multiple gates. So the matrix will be changed to 8. It is the 2 by 2. Okay. So we are having here as 4 by 4 matrix. And controls Z, this is also performed on the 2 qubits. So we are using the same 4 by 4 matrix. So in the control C naught, only the bit will be flipped, whereas in the control Z, the phase will also be flipped. That's why it is donating with the -1. So we have the swap. This is the gate where the states will be exchanged. For Toffoli, we are combining with the three qubits. So it is working the operations on the three qubits. The Toffoli is represented with the CC naught. These are the some notations, or CCX and the top. You can see the matrix here. This is the 8 by 8 matrix because we are using the three qubits. So 2 power 3 is 8. So we are using the 8 by 8 matrix. Next one is we are having the quantum gate features. This is the another some of the main features of the quantum gates. First feature is the superposition. So when we are concentrating on the old one, that is the classical logical gates. So in the classical logical gates like the and or not, these gates, the superposition feature is not implemented, and this feature is implemented only in the quantum logical gates. So this superposition can be done by using the gate called H gate, which is known as the Amadour gate. So here we are using this feature such that the superposition of the qubit can be changed. Okay, so this feature is not implemented in the classical logical gates. It's concentrating only on the quantum gates. Next one is another property or the feature entanglement. This entanglement is also not implemented in the classical logical gates, but this feature is implemented in the quantum logical gates. So this entanglement can be created by using the multi-qubit gates, like we have the C naught where we can use uh, 2 qubit or 3 qubit. Like this, we can use the multi-qubit. Next one is the reversibility. So the class in the this reversibility feature in the classical diagrams is not practically implemented. It is only implemented in the theoretical aspects. The same thing we are concentrating on the quantum gates. So in the quantum gates, we are concentrating on the another property called reversible, such that it will be used in the two options. Next one is unitary evaluation. So this unitary evaluation is the matrix representation where VS is very unique to the quantum mechanics. This quantum mechanics where we are concentrating on preserving the maximum probability of the total design format. Next one is some of the applications of the quantum gates. So here there are some applications which we are having here. The first one is the quantum error correction. This is the one option available here. So in this, whenever we are concentrating on the quantum logical gates, as we have discussed that the conventional classical, we are having some problems that the heats will be changed. So similarly, when we are concentrating on the qubits means the more number of bits. So there are chances that more errors may occur. So to avoid this one, we are having these quantum gates are used. So errors occur in the quantum logic gates due to the fragile nature of the charged items and their delicate interactions with the physical world. So in the chemical analysis, we have in the electron, proton, neutron. Okay, these are some charges we are having. In the electron, we have the negative. In the proton, we have the positive. Neutron, the neutral. Okay, so depending on the charged items, anions and the cations. Okay, the positive charged items and the negative charged items. If it is exposed to the physical world, there are chances that the state will be changed. Okay, so some errors possibility will be available. Okay, so that error correcting codes will be corrected by using the uh, this quantum gates. This is one of the application where we can implement the quantum gates such that to maintain the integrity of the quantum information and the codes can be fixed. Next one is second one is quantum simulation. So depending on the same charged item, there are some situations where the behavior of the quantum system can be changed. Okay, so the logical gates are applied such that the physical effects to the charged items and the simulation of the behavior of the quantum systems such that the further research can be done in the to the complex quantum phenomena, how the molecules will be interacted, what are the terms are used, okay, how it is interacted, how the behavior is changing, which are the factors which is affecting. All these are uh, implemented such that the simulation can be done and which are preventing the this type of disturbances. So this is the another chemical reaction by using this quantum simulation. We can design the quantum devices. This is the application of quantum gates, which will be concentrating on the application of the energy, the charged item, such that the gates will be useful in the research and the deployment of the quantum devices by using the from sensors to the communication devices. So how the quantum sensors, quantum communication devices will be helpful um, in this one. So we are using the one application device called the quantum device, where different sensors, quantum sensors, and the communication will be deployed such that the disturbance should be avoided. These are some other applications of the quantum gates. One is the quantum entanglement. This entanglement will occur when the two quantum particles will share the same quantum state. For example, if the particles are at a very far distances, okay, or the near distances, and they are sharing the same state, assume that are in the same positive state, okay, then at the time some problem will occur. Okay, so here these gates will be created and maintained such that these critical devices should not be done. How to overcome this one, it can be applied here. Next, quantum teleportation. This is the another one which is the extension of the quantum entanglement, which will allow the transfer of the quantum states across the larger distances, which will affect both the quantum communication and the quantum security. So these are some of the applications which of the quantum gates. Next, we concentrate the quantum circuit. Quantum circuit is a sequence of quantum gates which will be applied on the qubits. So when we are designing any circuit with the use of the quantum gates on the qubits, that the sequence of quantum gates in one diagram or one pictorial representation is known as the quantum circuit. These gates will manipulate the qubits quantum state through the different operations The main operation in the quantum computing is the reversible, because the qubits are exhibit the reversible states, and these will be governed or controlled by the quantum mechanics principles. So the quantum circuit will be designed by combination of multiple gates, see, quantum gates, which will be applied on the qubits. It is in the sequence using on the single qubit or two qubits. How depends on the demand of the situation of the demand of the real time problem or the scenario. The unique features of the quantum circuits are, the first one is the superposition. So in the quantum computing, we have this superposition. Qubits can be in multiple states at once. Okay, this is the unique position. As we have discussed, the gates, the Hamadad gate will be used for the superposition. Next one is we have in the entanglement. So this entanglement is the another property of the quantum circuits, which will correlate with the classical bits, such that the qubits will be uh, entanglement. Here we are not applying any copying, which is known as the no cloning. So you cannot copy an unknown quantum state. Reversibility, all gates are reversible, means it will mean the two-way direction can be done. Okay, except the measurement. So these are the some of the features which are very unique to the quantum computing. The main components in the quantum circuit is we have in the qubits. The first one is the basic unit of the quantum information, which can exist in the superpositions like alpha, beta, like this. Okay, so this is the qubits. Next one is we have the quantum gates. These quantum gates are similar to the classical logical gates with more extensions, more security features, or more we can say the quantum features. So this is the feature which will work on the qubits instead of single bit. Okay, we are working on the number of bits, which is known as the qubits. Measurement, this will be the state of the collapsing the qubit state into the classical bits, okay, which is the collapsing state. We call them as the decoherence property. Okay, so this is another option. And wires, which is the your representation of the evolution of the qubit state through the time. So as the interval will be time interval will be implemented, then we can use the different wires. So these are some of the main components or the key components of the quantum circuits. Next, we are having the quantum circuits simulation tools. So here we can use different tools which are available by on the quantum circuits. The first one is the Qiskit, which is from the IBM, and next one is the Circ, which is from the Google, Penny from the Xanadu, Bracket from the AWS, and these are the some of the simulation tools which you can use on the quantum circuits to for the real-time simulations before applying into the real-time applications. Next, these tools can be executed or run on actual the hardware related to the quantum computers. Okay, so the hardware already discussed in the session one. Okay, by the speakers. Okay, so depending on that quantum chip and quantum hardware, okay, the whatever the specifications are there on the quantum system, on those systems only these simulation quantum tools can be executed. So some examples here is from the IBM. We have the IBM Quantum Experience, Google, Sycamore, Rigetti, Anki, Qkera, some other hardware. So on this, these tools can be executed. Next one is we are having the quantum algorithms. So these quantum algorithms are the procedures which will be used to computation or to calculation, which will run on the quantum computer, such that to apply the quantum phenomena like superposition, entanglement, and interference to solve the problems in different formats and very faster compared to the classical algorithms. So quantum algorithms are designed in such a way that these algorithms are very faster, okay, and which are uh, designed for the quantum computers implementing the quantum phenomena to do the computations. These quantum algorithms will offer the exponential speedups, okay, which will others will apply in the modestly, but these are the unique power of the quantum computing. So the speedup will be very exponentially instead of the gradually. So these are the algorithms which are specially designed for the quantum computers. A few algorithms which are very famous, are very popular, are listed here. We will discuss later. Before going to that, what are the main principles of the algorithms? So for the quantum algorithms, the key principles are the first one is the superposition, as we are familiar with the superposition, which will allow or to explore the qubit into the multiple states at the once. Next one is entanglement, okay, which is the correlation for the different protocols. Interference, which will amplify the outcomes, okay, which is the if the any option is incorrect or the wrong, it will be cancelled, okay, and the outcomes will be amplified. Measurement, the collapsing between the state, the how the collapse the quantum state is collapsed into the classical answer, that is the measurement. So these are the four main principles which are associated with the quantum computing algorithms. So these are the main features implemented in the algorithms. The first algorithm, which is very popular here, we have in the Grover's algorithm, and this Grover's algorithm was developed in the year 1996. This will perform the unsearched searching. That is, if you want to do searching to find any item in the unsorted database, okay, assume that if you are collecting the bulk data like from the data from the Facebook, social media, any social media analytics, so assume that those are not in the structured one. Those are the not properly arranged. So in those unstructured, unsorted database, okay, the search will be performed. Okay. So here the complexity will be different. Okay. In the classical, we have the order of n it is, okay, and in the quantum computing, you have the different complexity. Okay, so the use case is we have in the speeding technology because the quantum algorithms are designed to do the computations very fastly compared to the other systems. So here there is a use case that if the brute force search like the password cracking, the usually we guess the passwords to crack the password. This may be this format by using the brute forces. Okay, so instead of brute force, you can use this reverse algorithm such that you can speed up your all the analysis and the searching technologies. Next one is the Shor's algorithm. So in the Shor's algorithm, this is developed in the year 1994. Okay, the main problem was the integer factorization. Okay, so where you are finding the multiple factors for the large numbers. Okay, So if you want to find the factorization for the large numbers, the complexity will increase. Okay, so in that case, the quantum Shor's algorithm is a very best algorithm where the complexity is also polynomial in the quantum complexity. And here we are using the breaking of the RSA encryption, where the breaking will be done theoretically depends on the different cryptographic systems. Just I'm giving the overview of the algorithms. I'm not going in the depth of these algorithms. Okay, how many algorithms are there and for what purpose the main use is available? Only the overview of the algorithms are presented here. Okay, not the complete depth explanation of the algorithms. Next one is we are having the quantum Fourier transform algorithm. This is the another algorithm where the core will be used in the source algorithm and in the phase estimation. So this will allow the transformation of the frequency domain, like which we did in the frontiers Fourier transformation in the classical computing. Okay, so the FFT is in the classical designing algorithms. That system is updated in the quantum computing by using the QFT algorithm, quantum Fourier transform algorithm. Okay, and this is enabled to detect the periodicities in the different quantum states. Next one is quantum phase estimation. So this is the another algorithm which is used in the Shor's algorithm, quantum simulations, and is solving linear systems. The main purpose of this algorithm is to estimate the phase or the eigenvalue of the unitary operator. This is the main purpose of this estimation algorithm, and these will be the basis for the more advanced algorithms in the different areas like the chemistry and the material sciences. So in these two areas, whenever we are using the advanced algorithms, this QPE quantum phase estimation will become the basis for these advanced algorithms. Next one is we are having the Deuce algorithm. This will determine whether the function is the constant or the balanced with a single query. So this is used to perform the function. We implement the functions here to check whether the function is the constant function with the query or it is balanced. Next, in the classical complexity, we require the multiple queries, but in the quantum, we require only the one evaluation. The significance of this algorithm is that in the quantum speed, only the first one of the first examples of the quantum speed up will be considered. Next, variational quantum algorithms, which is the both quantum and the classical processing. This is the hybrid algorithm, which will use both technologies or both processing, the classical processing as well as the quantum processing. Some examples of these variation quantum algorithms are VQE, variational quantum eigensolver. This is the algorithm which will be used in the chemistry and the material science. Next one is a QAOA, which is the quantum approximate optimization algorithm, which is used for the optimization problems. And these algorithms are also suitable for the devices called the noisy intermediate scale quantum NISQ, where will be better. Okay, so these are the some of the principles of the quantum algorithm in the different fields and the different areas. Whenever the quantum algorithms are considered in the field of cryptography, then we can use the breaking of the RSA into the by using the Shor algorithm or the quantum key distribution. In the chemistry field, we can use the simulating molecules by using the VQE. Okay, that is the variational Turing estimation. Okay, QPE. Next, in the finance, we have the different portfolios. Okay, if you want to perform the optimal solutions in those areas in the finance, we have the QAOA. This is the algorithm, okay, which can be implemented in the finance area such that the optimal values can be obtained in the portfolio optimization, option pricing. These are some of the use cases or the examples in these areas. Compared to the logistics, we are using the again QA optimization, okay, route optimization, scheduling, okay, how the scheduling can be done, what is the different routes, possibility routes are there, which route will be optimal, less congestions. All these can be considered by using the QAOA algorithms. Next one is machine learning area. In the machine learning area, we have these algorithms which will be concentrating on the quantum classification, like the data classification can be done by using the quantum enhanced data classification, the different methods called the kernel methods. So these are the some of the use cases in the different areas available in the world. So these are the some of the references which are used in preparation of the option here. Okay, this is the thank you very much for giving me the opportunity to present the session. Thank you very much, ma'am, for giving me the opportunity and for all the participants for their cooperation and the patience for listening me. Thank you very much.